All right, guys, welcome to section 3.2. We are going to be looking at the product rule and the quotient rule. So we just got done looking at a constant rule for taking the derivative, an addition rule, and a subtraction rule. And now we get to do a product rule and a quotient rule. Okay, so right off the bat, let's get this out of the way. The product rule, so it's when we would be taking the derivative of a product of two functions. So maybe something like that. It does not equal the product of the derivatives. That's not how we find the products of the derivative of a product of functions. So this is what we're going to do. The formula is a little bit different. So we're going to derive the formula. Again, it's a little bit more abstract, but that's the goal of this calculus sequence, is to get us to thinking a little bit more abstractly. So let's see how we can derive this formula and where this formula is coming from, all right? Because we want a good justification, because this is pretty intuitive, but that's not how we get it. Okay, so area is normally interpreted as a product. So we're going to interpret, or area is a product rather, we're going to interpret the products of f times g as an area. Okay, and this is how we're going to do it. We're going to let our variable u equal our f of x function, and we're going to let v equal our g of x function. Okay, so then if we take f times g, that's the same as u times v, oops, on some sort of rectangle, and then the area inside would be your u times v. U times v. Okay, so if we're going to take the derivative of f times g, that means we're going to take the derivative of uv. We're going to take the derivative of the area. So the derivative, remember, it's like a rate of change. So if we're taking the derivative of an area uv, that's going to be interpreted as the rate of change of an area. All right, with respect to x. With respect to x. So the derivative of uv with respect to x, okay? And here's some other notation. Remember when we talk about change? Just for now, I'm going to interpret that with a triangle or a delta. So let's do change of uv, how quickly that is changing, and compare it to how quickly x is changing, all right? Because look over here, u and v are functions of x. All right, so what's all of this going to look like? Well, let's redraw our rectangle. Let's see if I can draw a little bit better this time. That looks nice. All right, so we'll have u and v over here. Okay, and then let's do the change of both these things. No, there goes my nice square, but that's okay. So if we're going to change the area, we're going to change the rectangle, right? We're going to make it either bigger or smaller. So in this case, I made it, our rectangle, get bigger. So this side right here would change by v, and then this side right here would change by u. Okay, so let's talk about the change in x, because that's what this denominator is. So right here too. So there we have the change of our area, right? We made our box a little bit bigger. And now the change in x is that delta x. And remember, u and v are a function of x. So change in x, that delta x, is going to affect the change in u and change of v, because remember, u and v are functions of x. And so what we're going to do is remember that this u is equal to f of x and v is equal to g of x. So let me write that there, because now we can talk about change in u and change in v. So the change of u is if we add that change of x and then subtract the f of x. Okay, so this whole thing right here is acting as f of x plus delta x, something like that. Okay, and then likewise, v is doing something like this. Don't do it. All right, so we're going to focus on, so this is like our setup of the situation we've created. And now we're going to focus on the change of area. Okay, so the change of area going from this black rectangle and then extending to the black rectangle plus the blue. And we can kind of see, before we even start writing things down, that the change in area is this stuff, right? This is how the area is changing. Okay, so that's where we're at. Let's talk about it. So we'll do that color. Change in area. Remember, we're calling area u times v. So the change in area would be delta uv. All right, so how that's changing. So what we're going to do is we're going to take this whole length, which is u plus delta u, and we're going to multiply it by v times delta v. And that's going to give us this whole area. And then we're going to subtract our original rectangle. And then that's going to give us that highlighted part. So let's write that out. All right. Remember, the point of this is we're trying to prove our new product rule for derivatives. And we're getting there, okay? All right, so there's our change in area. Let's simplify that. We're going to FOIL it out. So let's see. UV first, then minus UV. That's going to cancel right off the bat. And then I'll continue on with my FOIL. U delta V plus V delta U plus delta U delta V. Okay, there you go. So once we have the change in area, to get back to the derivative, let me go up, 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 up. Remember, we want to get the derivative of a product. We have to take it with respect to x. Okay, so we're going to look at the change in area and compare it to the change in x. All right, so essentially we're just going to go through and divide everything by the change of x. All right, so that's going to give us a rate of change. Okay, so that's going to become the derivative. And it's going to become the derivative as the change of x approaches 0. So as the change of x approaches 0, we get the derivative of uv. And if we get the derivative of uv, that's the derivative of the product, f times g. Okay, so let me write that out. We would write that in mathematical terms. Whoops, I can do that better. We would say that the derivative of uv is equal to, if we want delta x to approach 0, that's a limit. So we're going to take that limit of the change of uv over the change of x. All right. So that means we're going to take the limit of all this stuff as delta x approaches 0. So when we take the limit, and it's the sum of a limit, remember we can distribute the limit to each term. So let me just write out that step. Okay, good. And then we're almost done. So let me point out this. This limit is dependent on delta x, right? Delta v has a delta x in it. Let me show you. That was this. Remember, delta v is dependent on delta x. Delta u is dependent on delta x, right? So when we're taking the limit as delta x goes to 0, that's going to affect these two terms, but it won't affect u. So we can move u to the outside. And same argument over here, we can move v to the outside. All right. So let's see what we get. So moving the u out, we have this. Moving the v out, we get this. All right, and then here we have that delta x, right? But remember, if delta x is going to 0, we can just kind of separate this out a little bit. It means delta u is also going to go to 0. And so this whole thing is going to end up going to 0. So we're just going to write a 0 right there. Because everything's going to 0, right? The delta u that's going to go to 0. So we're almost there. So we are taking the derivative of u times v, which is f times g, if you remember. And we have our u here. Let's write out this again. So we have the u. And then this is just the derivative of v with respect to x, right? Because remember, this delta is a difference. So I'm going to write dv dx here. Change of v over the change of x, that's exactly what it says, plus v times the change of u times the change of x. Okay, so we were trying to find a derivative of a product. It seems like it would be u prime times v prime, but look, if we interpret it as an area, it's a lot more complicated than that. So with that kind of brief justification, we can now talk about the product rule. Okay, so let's start off. If f and g are both differentiable, then we have that the derivative of their product, so we'll go f of x times g of x, is equal to, let's see, the first function times the derivative of the second, I'll write it like that, plus the second function, times the derivative of the first. Okay, and this is a formula to definitely memorize. And I also sometimes, because it's addition, it doesn't matter the order of these two terms. So sometimes I'll do the second function times the derivative of the first. Right? It doesn't matter because with addition, our terms are commutative. Okay, so good. So we have another Another theorem to memorize. That's our product rule. So let's see this rule in action. All right, so let's say we have a function and we wanted to find the derivative. All right, let's say it's df dx. Okay, so let's look at this. So we want to find the derivative, and what do we notice about the derivative? Excuse me, what do we notice about the function? We have a product. So that tells us that we have to use our product rule. Okay, and then notice even if we were to simplify this and distribute that e to the x, we would still have a product, x cubed times e to the x. So no matter how we slice it, we have a product. All right, so we have to identify our two functions. So we can call this first factor f, and we'll call the second factor g. All right, and then remember how the formula goes. We can do g times f prime plus f times g prime. Okay, let me write that a little lower. Okay, so our formula tells us that we can do g times f prime plus f times g prime, or vice versa. It doesn't matter. We'll get the same answer. Okay, so tally ho. G is e to the x, so we'll leave it like there, like that. And then f prime. What's the derivative of x cubed plus 1? Here, I'll write it out like this since it's our first time. Good, 3x squared. Okay, so e to the x, the derivative of x cubed plus 1, that's our exponent rule, our power rule. And then what's the derivative of a constant? It's 0. So that's that. All right, and then over yonder, we have this. That stays the same. What's the derivative of e to the x? It's e to the x. We saw that in section 3.2. Okay, so that's that. We can clean it up a little bit. For instance, we can do this multiplication and we can move the coefficient out in front. It's kind of standard. So we can write it like this. That's all a product. And then here we can distribute the e to the x. So we can have something like this. All right. And then after you do this, sometimes your textbook will factor it, but I'm going to be okay with either form. If you use the rule and simplify, I'm okay with that. Okay, and you can even take it a step further. Once you take out that e to the x, you can even write your polynomial in standard form. All right, so different ways to express our solutions. All right, so why don't you guys try some product rule examples? I'm going to give you guys two, and then push pause, and then come back and see the solution. So again, the instructions would be to find the derivative, or find f prime, find df dx, something like that. And you guys, here's your first function. And here's your second. All right. Let's see how you guys did. So we're going to find the derivative. Let's looking at this first function. We definitely have a product. So we have a product rule. That's perfect. Let's see. E to the x, we know how to take that derivative. What about the square root of x? What can we do for that to help us solve it? Good. We have a power rule, an exponent rule. Whoops. So we could write that square root of x as x to the 1/2. And then we can find that derivative, okay? All right, so then now that we have that, we have all the rules we need for that. That's going to require 3 rules. Isn't that bananas? Okay, so f prime of x, we are going to, we can write the first function. I'll switch it up because with the product rule, order doesn't really matter. Take the derivative of the second function, and then second function times the derivative of the first function. All right, and then we simplify. What's the derivative of e to the x? E to the x. And then how do we do our power rule? When we take the derivative, the exponent comes down, and then we subtract 1 from the exponent. So 1/2 minus 1 is negative 1/2. All right, so what can we do to clean this up? Well, let's see. We started with square root signs, so I'm just going to rewrite x to the 1/2 as the square root of x. And then we have a negative exponent. It's always nice to make negative exponents positive, so we'll send the x downstairs. And it has company downstairs, right? The 2 is in the denominator. So we can write it like that. That's a nice simplified form. All right, so there you go. Okay, number 2. We can actually solve this 2 ways. The first way, let's use our product rule because we see that there's 2 factors, right? So we can use our product rule since we're multiplying. So again, our product rule tells us that we'll switch it up again. We can take second function times the derivative of the first. And again, we can switch it up because the product rule uses addition. Plus the first function times the derivative of the second. Okay? All right, tally ho. Derivative of x squared plus 1. There's our power rule again. Bring down the exponent, subtract 1 for the new exponent. What's the derivative of 1? Constants are 0. Okay, and then over here, what's the derivative of x? It's just 1. All right, and then we actually have a theorem for that, but if you wanted to, because it's kind of fun to do things different ways, we could even use the power rule for that because x is just like x to the first. So if we take the derivative, we bring down the 1, and then we subtract 1 from the new exponent. 1 x to the 0, well, x to the 0 is just 1. 1 times 1 is 1. So we have 2 ways to solve that. So cleaning this up, 2x squared, and then x squared plus 1. We have some like terms. X squared plus x squared is 3x squared. All right, there you go. Anybody solve it differently? There's another way of solving it. And that way is by distributing the x. And when you distribute the x, you can just use the power rule. So then the derivative, make sure you write f prime of x so we know what you're doing. Bring down the exponent and subtract 1. What's the derivative of x? It's 1. So different ways to do things. Some ways are more efficient than others, for sure. All right, so let's take a pause here, and then our next video is going to be on the quotient rule.